Talk about Chapter 4, Atoms and Elements. Atoms are the foundation of our sensations. Typical seaside rocks are composed of silicates, which are compounds of silicon and oxygen atoms. The seaside air contains nitrogen and oxygen molecules. Seaside air might also contain something called amines. And the amine shown here is triethylamine, and it is emitted by decaying fish. Triethylamine contributes to the fishy smell of the seaside. Atoms are incredibly small. A single pebble from a shoreline contains more atoms than you could count. The number of atoms in a single pebble far exceeds the number of pebbles on the bottom of San Francisco Bay. To get an idea of how small atoms are, imagine if every atom within one small pebble were the size of the pebble itself. That pebble would be larger than Mount Everest. So atoms compose matter. The properties of atoms determine the properties of matter. An atom is the smallest identifiable unit of an atom. An element is a substance that cannot be broken down into simpler substances. There are about 91 different elements in nature, so therefore there are 91 different kinds of atoms. Scientists have succeeded in making about 20 synthetic elements. The exact number of naturally occurring elements is controversial because some elements previously considered only synthetic may actually occur in nature in very small quantities. Democritus and his mentor Leucippus recorded their idea of atoms. Democritus suggested that if you divide matter into smaller and smaller pieces, you will end up with tiny, indestructible particles, and these would be called atoms. He called them atomos, which means indivisible. Okay. Democritus was the first person on record to have come up with the idea that matter is composed of atoms. And then here's a picture of just how somebody imagined back in the day of Democritus and Diogenes. So over 2,000 years later, John Dalton formalized a theory of atoms that gained big acceptance. So Dalton's theory of an atom has three parts. The first one, each element is composed of tiny indestructible particles called atoms. The second one, all atoms of a given element have the same mass and other properties that distinguish them from the other atoms of other elements. And third, atoms combine in simple whole number ratios to form compounds. So later on, there was J.J. Thomson, and he discovered the electron. So he found that electrons are negatively charged. Let me get my pen going. Are negatively charged. Electrons are much smaller and lighter than atoms. Electrons are uniformly present in many different kinds of substances. He proposed that atoms must contain positive charge that balances the negative charge of electrons. So in his model of the atom, he suggests that the electron is negatively charged, that's the yellow part here, and it is held in a sphere of positive charge, the red part here. Okay. All right, so later than that, there was Rutherford, and he found something to add to the previous model. So there was Rutherford's gold foil experiment, and this was in 1909. And in this one, there were alpha particles that were shot through a piece of foil, okay? And for the most part, the alpha particles would just go through to the other side, okay? Over and over and over, go through to the other side because they're alpha particles. And in the previous model of an atom, that's what should happen because there's nothing inside that's really dense that would stop the alpha particles. So after doing several experiments of shooting these alpha particles through the foil, occasionally one or so here and there would start deflecting back in the other direction. Okay, so picture this like if you're going shooting and you're shooting through a piece of paper, shooting through a piece of paper, shooting through a piece of paper, and it's going out the other side, and all of a sudden, one time your bullet comes back. Okay, so when that happened, he knew that there had to be something dense inside of the atoms that was causing that deflection. And that is how he came up with the nucleus. So in the plum pudding model, you would see here that the alpha particles would just go all the way through, okay, over and over and over. But when he did the alpha scattering experiment, the Rutherford experiment, he found that in fact the alpha particles ended up hitting something, and so the alpha particles ended up deflecting back, and so that's how he came up with the nucleus. All right, so here's what this sums up what Rutherford found. Most of the atom's mass and all of its positive charge are contained in the small core called the nucleus. Most of the volume of the atom is empty space through which the tiny negatively charged electrons are dispersed. The number of negatively charged electrons outside of the nucleus are equal to the number of positively charged particles, which are the protons, inside of the nucleus. So the atom is electrically neutral. So if you look here in this image, they enlarged the nucleus so that you could see it, and they made the electrons look like particles. So 99% of the atom's mass is contained in the small dense nucleus, and then in the nuclear model, the atom is mostly made up of empty space. The nucleus contains your proton and your neutron. Talk about the relative size of a proton and an electron. If a proton has a mass of a baseball, an electron would have the mass of a grain of rice. The proton is nearly 2,000 times as massive as the electron. Electrical charge is a property of protons and electrons. Positive and negative electrical charges attract one another. Okay, positive and negative charges repel one another, and positive and negative charges cancel each other out. So a proton and an electron, when paired, are neutral in charge. Out of your book, and it just shows the relative masses of protons, neutrons, and electrons. You'll see here that the protons and neutrons have similar masses, and electrons have almost no mass. So you might use this table when you're solving homework problems. An electrical storm provides evidence of charge in matter. So matter is normally charge neutral, having equal numbers of positive and negative charges that exactly cancel. In an electrical storm, the charge balance of matter is distributed. So the quick rebalancing of charge often occurs in dramatic ways like lightning, you see here. All right, how atoms of elements differ from one another. So elements are defined by their number of protons, okay? It is the number of protons in the nucleus of an atom that identifies the atom as a particular element. If the atom had a different number of protons, it would be a different element. The number of protons in the nucleus of an atom is its atomic number, and they just give that the symbol of Z. So helium has 2 protons, so its atomic number would be 2, and aluminum has 13 protons. And remember, your protons are in the nucleus. So aluminum's atomic number would be 13. If you take a look at the periodic table here, the periodic table lists all of the elements according to their atomic numbers, okay? So we have 1, and then 2, 3, 4, goes all the way across. The number on the top is its atomic number, And then the number down low is the atomic mass. So the one that we're looking at here is beryllium, and it has 4 protons. Most chemical symbols are based on the English name of the element, but some they won't seem like they make sense, and that's because they're based on their Latin names. So for instance, potassium does not have the symbol of a P, it has a symbol of a K, and this is because of its Latin name Kalium. And the symbol for sodium is not S, it's Na, and this is from the Latin name natrium. And then there are some others that are named with Greek names. Generally, like you will have, like say carbon, it uses the large C for carbon. And then since that's already used, when they went ahead and used this, made the symbol for calcium, they did the first big letter of C and then they used the next letter, so Ca. So just to kind of see how they came up with a lot of those symbols. But here are some others. Lead is not a large L, it's Pb for plumbum, and then we have mercury, hydrargyrum, not really sure how to pronounce that one. Iron, ferrum, silver is Ag, okay, tin is Sn, and copper is Cu. Let's see here. I'm not really interested in that one. Okay. Curium is named after Marie Curie, and she was a chemist who helped discover radioactivity and also discovered 2 new elements. She won the Nobel Prize for her work. And bromine originates from the Greek word bromos, meaning stench, and it's because it has a really strong smell. Mendeleev, he suggested that we arrange the elements on the periodic table in order of increasing relative mass because certain sets of properties recur periodically. Okay. This is just a picture just showing the properties that elements have, and so the when the periodic table is organized with those properties in mind, you'll notice that the vertical columns, the elements in the vertical columns will have similar properties. So the elements on the periodic table can broadly be classified as metals, nonmetals, and metalloids. So basically on the left-hand side of this stair stepper here, you have most of your metals. On the right-hand side of the stair stepper, you have most of your nonmetals. And then along the stair stepper here are your semimetals or metalloids. I think I have time for one more slide here. Metals occupy the left-hand side of the periodic table, and they have similar properties. Metals are good conductors of heat and electricity. They can be pounded into flat sheets. That means they're malleable. They can be drawn into wires. They're ductile. They're often shiny. Metals tend to lose electrons when they undergo chemical changes. And good examples of metals are iron, magnesium, chromium, and sodium. Occupy the right-hand side of the periodic table. Remember the dividing line is that stair stepper there. Nonmetals have varied properties. Some are solids at room temperatures while others are gases. As a whole, they are poor conductors of heat and electricity. They tend to gain electrons when they undergo chemical changes, and good examples of nonmetals are oxygen, nitrogen, chlorine, and iodine. It's also called semimetals, have mixed properties. They are also called semiconductors because of their intermediate electrical conductivity, which can be changed and controlled. This makes them useful in manufacturing electronic devices that are central to computers, cell phones, and modern gadgets. So silicon's probably one that you've heard of most commonly. The rest of this chapter in the next video. Awesome job.